Next up, we have Litao Zhou talking about full Iso-recursive types.
Thank you for the introduction. This talk is about full Iso-recursive types. My name is Litao Zhou, and this is joint work with Qianyong and Bruno Oliveira from the University of Hong Kong. So to give you a background, let's start with recursive types. So recursive types are useful for defining recursive data structures or expressing recursive objects. So like here is a data type list, which is recursive defined in a way that you have this list in the const constructor. So you can encode it using recursive types, where this recursive occurrence of list is represented as a recursive variable alpha, bounded by this recursive binder mu. And you can do unfoldings for recursive types by substituting the recursive variable with the whole recursive type. Like you can do one-time unfolding, two-time unfolding, and so on. And depending on the way you treat your unfoldings in your type system, there have been two ways to approach recursive types, iso-recursive types and equi-recursive types. So iso-recursive types treat recursive types and their unfoldings as equal, not as equal, but isomorphic. So for example, you have this in-L unit that can be directly typed as the unfolded type. But in order to get its recursive type, you need to insert a fold operator before the term in order to do the transformation in the ISO system. So this can be described by this typing rule, where you have this fold constructors in your term language that does the folding. And on the other hand, equi-recursive types do not have this unfold and folds. So you can type a term that any types that are equal up to infinite unfoldings. So they have this special type equality relation that allows you to equate between recursive types and their unrollings. And usually this rule is defined co-inductively. So in addition to relating them between unfolded types and types, you can also equate it. You can also type this term without annotations to a different shaped recursive type, but are equivalent to the list recursive type up to infinite unfoldings. So as we see, iso-recursive types are, with this explicit term level unroll and roll annotations, you get a simpler meta series usually. And it is also easier to work with when you want to extend it to other features. But that's not the case for equi-recursive types. And but equi-recursive types gives you convenience in programming. So with all these pros and cons, a natural question is, what is the relationship between these two formulations? And back in the 90s, Abadi and Fiore, they managed to show that these two formulations are equally expressive in terms of typing. So one term that is well typed in one system, you can translate it to the other that has the same typing. So the easy direction is from iso to equi, where you just erase the fold and unfold annotations. But for the other direction, they show that inserting fold and fold are not enough. You need to have explicit coercion functions. I will detail this in a few slides. But they show that, but they managed to show that for all the equi-recursive type equalities, you can always find an iso-recursive term, which is a function that can be considered as a coercion that achieves this transformation. So by inserting these coercions into the equi term, you get a well-typed iso term. But they did not consider an operational semantics in their work, so there is no formal guaranteeing that this translation preserves the behavior, such as termination of the terms in the translation. And more recently, Patrignani and other people, they show one semantic result that from iso to equi, this erasure translation is semantic preserving, behavior preserving. Actually, they show that it's a stronger result, that they are fully abstract, that preserves the contextual equivalence between terms. But they also did not consider the other direction. So regarding this question, our paper tries to address this problem from a different perspective. So we propose full iso-recursive types as a generalization of iso-recursive types that subsume the typing and behavior of iso-recursive types. And we prove that our new formulation is sound and complete to the equi-recursive type system in terms of both typing and behavior. And so before we introduce the details of full iso-recursive types, let's first take a look at why encoding equi-recursive types in iso-recursive types is complex. So let's consider a term t, which originally can be typed as a two-arity function, int to a recursive type. So this part of the recursive type can be folded, partially folded to the recursive type. So you can get this typing in the equi type system. And in order to encode this typing in the ISO system, you have to insert a coercion function, which basically inserts a fold operator on the application of result of applying this t to a integer argument, which has the integer type. So after this fold, you can get the type. And this encoding loses an important property, which we call round tripping, which basically says by erasing this unfolds and folds from your encoding, it does not necessarily give you back the original equi term. So with this example, you need to reason that this function application has the same behavior as the original term, although it is clear here that they're equal to beta and eta expansion, but you can imagine with larger programs, this semantic reasoning can be quite complex. And our observation into this problem is that it's a result from the limitation of standard ISO recursive type formulation, that it only allows you to do unfolding and folding on terms that have a recursive type. So basically, you can only transform on terms that are of recursive type, and you cannot insert this unfold fold anywhere in a term, to achieve this partial folding. So our solution is also simple. We generalize the fold and unfold operator in the ISO type system to a cast operator that not only allows you to do fold and unfolds, but also you can do more complex, deeper nested transformations. For example, you have this cast of functions that allows you to do deep transformation on a function type. And so with this, our previous encoding problem in the full ISO type system, all you need is a cast operator. So its input argument is an identity cast that keep the integer as it is, and it transforms the output type to fold it to a recursive type. And you can see that erasing these cast operators gives you back the same original term in the equi system. So later you will see it will help with our semantic preservation reasoning. And so in order to type these cast expressions we introduced, we define a set of typecasting rules, which is standard just by structural induction on the cast operator. So it just basically describes what a typecast operator can transform between two types. And from this, you can see that iso-recursive unfold and folds, the typing rules, are just syntactic sugar in our, you can use these atomic cast operators to encode them that achieve the same effect of typing. And in the paper, we have more cast operator to handle more complicated mechanisms in equi-recursive type equalities like co-inductive reasoning. But the takeaway is that our type casting rule is sound and complete to the equi-recursive type equality rule. And with that, we can define a type-directed elaboration rule, which just generalizes the equi-recursive typing rule with a full ISO term and we replace the equi-recursive type equality with this new typecasting rule that generates a cast to describe this explicit cast to describe the type transformation, and we can generate correct full ISO terms that can preserve the typing. And with the help of this elaboration rule, we can state the soundness and completeness of our full ISO typing with the equi-recursive typing, which says that for all equi-recursive well-typed terms, you can always find a encoding in the full ISO system that achieves the same typing. So that's it about typing. And then let's talk about semantics. So we have this new cast expression, so we need to define new semantic rules for them. And first we extend the values to include two kinds of cast. One is the fold cast, This is the same treatment as iso-recursive type system that treat fold expressions as values. And we also define cast of functions to be values, because basically you cannot further reduce them without applying a function to another argument. And our rules are small step call by value. So for cast expressions, the inner expressions are first reduced, and identical casts are eliminated. And just the same as the ISO type system, you can cancel pairs of unfold and folds to get the value if you have this in your computation. And the more interesting rule is the push rule for functions. So in our new system, since we have this function cast as values, the canonical form of a function type can not only be a lambda, but also be this new function cast. And we need to define semantic rules to ensure their progress when it's applied to an argument. So here's our design, which is, we call it push rules because it is inspired by similar designs in the GHC compiler core language, system FC. Basically it decomposes this function cast into smaller casts and apply the input cast to the incoming argument, v2, and apply the output cast to the result after application. And in order to ensure preservation, we have this special operator that reverses the direction of fold and unfold just to ensure preservation. So if you recall our previous example, the encoding, if you apply it to an argument integer, then based on this rule, the identical cast will be applied to the incoming argument, and you reduce it to 1, and based on the result of t applied to 1, you can do further reductions, and you can see that it is preserves the typing, so this can give you a sense of progress and preservation in our system. So that's it about type safety. And then let's see how our full ISO system has the same behavior as the equi system. So the direction from full ISO to equi is also simple. We erase the cast operators. And since our rules are designed in a way that are computationally irrelevant, so you can just safely erase them. So if you start with a trace in the full ISO system, if you erase all the cast operators, that also holds in the equi type system semantics. And this theorem actually has an implication that our cast cause no runtime overhead. So you basically, in practice, you don't have to worry that the cast operators can get too large, because if you really want to evaluate our cast expressions efficiently, you can just erase them and adopt the equi-recursive semantics. And the other direction is actually also simple by induction. So the key observation is that we have this type-directed elaboration rule, so you can do encoding on it, and we can prove that for all the equi terms and the full ISO terms related by this elaboration relation, both of them have the same termination behavior. To summarize, this paper, we propose full iso-recursive types as a new formulation that generalize the iso-recursive type system with cast operators, and we extend their semantics with the push rules, and we prove type soundness of the system. And with that, iso-recursive types are just syntactic sugar in a full ISO type system. And by defining a type-directed elaboration rule that generate erasable casts, we show that our type system is equivalent to the equi-recursive types in terms of both typing and behavior. And all our results are mechanized in Cog. And in the paper, you can find another system that employs recursive subtyping, which is simple to extend. And as a remark for future work, we believe full ISO recursive types can be useful as an intermediate language if you want to compile a source language using equi-recursive types, because this explicit cast gives you information about type unrolling and rolling, so it will be beneficial for an internal analysis or optimization. And since our casts are runtime erasable, so you can erase them in your target language of the compiler to get efficient performance. And on the other hand, we also think we are also considering full ISO recursive type as a useful language design on its own, and we plan to extend it with other advanced type system features such as intersection types, polymorphism to give us interesting programming encodings. So that's all for my talk, and thank you for your attention.
Do we have any questions? Okay, I'll start with one. So does that mean now that you kind of, because before if you wanted equi-recursive types, you had to kind of go in co-inductive land, and that's not as pleasant as, you know, just staying with inductive types, that you can actually do that, and that you just, you know, have your equi-recursive types in your language and then automatically translate to fully iso-recursive, or are you in co-inductive land there too?
So actually, what I'm hiding from in this presentation is we have some more cast operators. Like you can do fixed points on a cast operator that can describe those co-inductive cyclic reasoning in equi-recursive types. So we are able to encode that. Actually, in the literature, you can find those papers that describe how to find this derivation. So you can essentially, in our paper, you can also derive this cast automatically based on these co-inductive rules. Yeah.
Any other questions? Oh, in that case, let's thank Litao.
Thank you.